Hello, my name is Mohammad Hashem Haqbayan. I'm currently a PhD student at University of Turku, Finland. The paper I'm going to present is entitled A Power-Aware Approach for Online Test Scheduling in Many Core Architectures. Recent advances in technology, fabrication process and computing architecture have enabled the integration of some hundreds of cores in the same chip, thus leading to the design of many core architectures. However, this trend has led to two main drawbacks. Due to increased power densities in the integrated circuit and related thermal issues, it is not possible to switch on all cores at the same time. On the other hand, the transistor shrinking is leading to devices that are more susceptible to internal defects, variability phenomena, and wear-out and aging process. Therefore, there is a quest for periodic test activities to assess the healthy status of the architecture and the absence of permanent failures. The main challenges of this activity are to limit the interference with the execution of the nominal workload, to do not violate the available power budget, and to consider multiple voltage frequency levels during testing activities, since failures may manifest only in certain operating conditions. Many core systems are not generally provided with hardware testing facilities. Therefore, functional software approaches such as the software-based self-testing may be an appealing solution. When considering the high performance demands many core systems are subject and the power limits of such architectures, it becomes particularly important to design an approach that is power-aware and non-intrusive. The goal of this work is to provide an answer to this quest. Moreover, as we will show, software-based self-testing is particularly able to adapt to the dynamicity of the many core working conditions and related resource management. As shown in this figure, the target architecture is a grid of homogeneous processing cores. This system is used to run highly parallel data-intensive applications, generally modeled in terms of task graphs. Moreover, since the workload is highly variable, with applications entering and leaving the system with an unpredictable trend, the loaded runtime resource management layer contains a runtime mapping unit that dynamically dispatches incoming applications, and a dynamic power management unit which distributes the available power budget among the various cores by acting on dynamic voltage frequency scaling and per-core power gating. In this scenario, we can schedule a test routine only if the suspect core is idle and there is enough power budget to execute the test. As it is possible to notice in the situation depicted on the left, even if there are almost a half of the cores that are idle, running applications consume all the available power budget. Instead, in the figure on the right, all the cores have been already allocated for applications execution. In conclusion, no test can be performed. However, the workload changes over the time. Therefore, the system may be in other situations in which both the suspect cores are idle and there is enough power budget to run the test. In such situations, two questions raise. Shall we use the available resources to run newly incoming applications or for testing purposes? In the latter case, which core shall we test? For these reasons, we extended the runtime resource management layer with a framework performing the online test scheduling. Its main goal is to maintain high system performance while guaranteeing the healthy status of the cores. The framework is organized in three main parts: a core's utilization monitor, an enhanced test-aware mapping unit, and a test scheduling unit. Monitoring cores utilization is performed by means of hardware performance counters integrated within each core. The rationale is that highly stressed cores need to be tested as soon as possible. Moreover, an aging monitor implementing a statistical reliability model helps in the identification of such stressed cores. Then the runtime mapping unit has been enhanced to be test-aware so that, if not strictly necessary for performance reasons, cores candidate for testing will not be allocated. Finally, the test scheduling unit checks if there is available power for testing candidate cores. Then among the candidate cores, the unit tests the one which is more likely to be used in near future allocation. The test scheduling unit selects also the voltage frequency level to be used during the test execution. A System C simulation platform has been developed to experimentally evaluate the proposed approach. State-of-the-art tools as Macbeth, Lumos, and Hotspot have been employed to characterize physical and architectural aspects of the system. Various experimental campaigns have been performed to demonstrate the efficiency of the approach. In particular, as it can be seen from these graphs, the approach presents a limited penalty on system throughput, at most 6% in highly test-demanding scenarios. Moreover, the approach is able to adapt the monitoring mechanism on each core according to the estimated aging of the core itself, thus avoiding unnecessary overtesting that would only cause a performance degradation. And finally, the test scheduler is able to accurately exploit the available power budget to run tests at all voltage frequency levels with a uniform distribution. In conclusion, we have proposed a new power-aware online software-based self-test scheduling approach for many cores able to quickly identify permanent faults and at the same time minimize the performance overhead and fulfill the available power budget. The experimental analysis has shown the effectiveness of the proposed approach in reaching the pursued goals. For additional details on the proposed test scheduling approach or on the executed experiment, please refer to the published paper. Thank you for your interest on our work.